Okay, give me a second. Okay, good. Yeah, so I guess so today we'll be wrapping up dynamic programming one. And we're going over a few problems just to get our brain working. And last week we talked about what we call recurrence relation, right? That's like at the core of dynamic programming. It's more like finding some formulas, finding some relation, and using that relation to solve your problem. So today I just want you to take a look at this question I just put in the chat. Product of array except self. It's just one link code, so you can just open the link in the chat. And I'm not asking you to solve. I just want you to look at the solution. One solution I just pasted also. So I'll actually go over the solution very briefly, just to it's actually very easy to understand, or you understand. And then I just want to once again hit on recurrence relation using this solution. So just open this question, the link in the chat, then paste this solution there and just take a good look at it for the next 1 or so minutes, and then we start. Sounds good? Sounds good? Okay. I don't know why no one wants
to.
Yes.
Yeah, all right. So let's do that. I've plugged my device to charge a bit. Let's hope it's charged now. Okay, just take a look at that for 2 minutes and then we start. Let me do the same thing here. Copy link. The question I came across some time ago where I think it's good. Okay, if you're done, you can react with an emoji or in the chat or something like done. Okay. Okay, so my internet actually ended up logging me out. That's exciting. Wait, are we done going through that? Can people hear me? Like I'm talking to myself. Okay. All right. Can someone put the solution I put into the chat? Okay, yeah, thank you. Okay, actually, I have it. Actually, no problem. Okay, let's start. We are behind time. So let's start. So we're going to touch on the concept of recurrence relation one more time. So when we went into dynamic programming the last time, we saw that the power of dynamic programming actually relies on the ability to, where's my screen share? On your ability to, what's this? Yeah, on the ability to derive a recurrence relation, right? So when we looked at the Fibonacci number, if you remember, all we needed was a Fibonacci sequence, right? So let me just open that Fibonacci. Or you even spell Fibonacci? Okay. Did we not solve it? Okay, let's just pick up a solution from someone. Yeah, so when we did the Fibonacci sequence, we actually said there were 2 ways of solving it, right? We talked about the bottom up and the top down, right? So we said this is actually a typical, top down. So from the top, that is Fibonacci of n, right? Let's just copy the solution and just paste it here. So we discussed that there are 2 ways of solving dynamic programming questions, right? One is top down, bottom up, and this is a typical top down. So from top down, we start with a bigger input n, right? And then we break it down, right? It becomes fib of n-1. It's obvious that n-1, right? n-1 here is less than n. So we are going from top, a bigger something to a small something. And n-2 is also bigger than n, right? So this thing here, what we call the recurrence relation, right? So recurrence relation is kind of like the only thing you need, right? Like these base cases come naturally to you. In an interview, the interviewer will even give you this, right, as part of the example. So this is what we call a recurrence relation. And much of the core dynamic programming, I feel like, lies on the ability to derive this, this recurrence relation. And once you have the recurrence relation, relatively easier, right? Now, this is what we call the top-down approach. Now let's look at the bottom-up approach. So if you look at the bottom-up approach, so the top-down is usually by recursion. We usually do it via recursion. Now, if you look at the, actually, let me put them side by side so that people can have a good look at both of them. So this is what we call the bottom-up approach. We usually do it using a loop, right, so iteratively. So as you can see here, this person's solution is a bit messed up. I probably should rewrite it. Let me just rewrite this guy. It's basically just how they've written it. All you have to do here, the person does not use list well, so it's simply memo of I. You can just use I here. Just use I here. They're reassigning the whole list, but that's not something you want to do. Memo of I is called memo of I minus 1, memo of I minus 2. Okay, so this is a bottom-up approach, right? So how do you do that one? It's actually a very similar approach, right? So first of all, you can add your base case. Can you ignore the base case and use this guy here? Then there are two base cases for the Fibonacci. As you can see, 0 and 1 is the same thing here, right? It's the same thing here. So think of this thing as storing your answers, right? This is what we call it DP, right? People usually name it DP or memo. Think of memo as some pad write your solutions on, right? So if I wanted Fibonacci of 0, I'd have given you index 0. Fibonacci of 1, I'd have given you index 1, right? That's basically how it is. Okay, so then you're okay, then from 2 going, right? From 2 going, so if I want memo of 2, if I want fib of 2, right? Fibonacci of 2, and they're it's simple. Just go and get memo of I minus 1, right? That is 2 minus 1, which is 1, right? And then memo of I minus 2, 2 minus 2, which is 0, right? And then you add them. And you realize that's actually the correct thing, right? You just get Fibonacci of I minus 1, then plus Fibonacci of I minus 2, right? Then the loop iteration. So when the first loop iteration, this guy, right, is going to change. So what they did here is kind of I know I just initialize, you can just initialize memo to be, let's say 0 up to n, right? So that's you get something like this. So if n is 4, you get 1, 2, 3, 4, right? Then from here, you initialize the first two. How do you write the code is just a bit, let's just initialize just 1, 2, 1. I'm just cleaning up their code. So now it becomes 0, 1, 0, 0. Right? Does everyone get this part? I'm just so this is as first initializing the whole memo, right? Here. So the reason why we're doing this is because you define what memo is. Memo is just going to be a list, right, of your solution, right? So if I want Fibonacci of 0, right, I'm going to just take the element at index 0. If I want Fibonacci of 1, I take this element, Fibonacci of 2 here, and I'm going up to Fibonacci of n, right? So Fibonacci of n is just going to give me this last guy. So that is just, just one way to think about it, right? So then, but Fibonacci of 1, right, is just going to be, 1, right, Fib 1. So if I want Fib 2, so as you can see, we start a loop at Fib 2. We're okay, so if I want this guy here, you probably want to make this 1 plus 1 or something. Then I just take the previous 2, then I add. That's basically what's going on here, right? So that's what we're doing here. So if we reassign, so this guy is going to be 1, right? Then if I come here, I'm going to be 1 plus 1, right? That's going to be 2. And as you can see, if I do 2 plus 1, that's going to be 3. If I do 3 plus 2, that's going to be 5, right? So that's what we call the bottom up. You start from, you start your list from some base case. And as you go up, you just compute it, right? You just use that formula, right? As you can see, it's the same thing here, that recurrence relation to basically build it up. And that is what we call bottom up. So this is what we call the bottom up approach, so we call the top down. Code wise, this is usually cleaner, right? But I think logic wise, this is usually easier, right? Thinking of it recursively, right? So this is the recursion we did, right? We did recursion 4 weeks ago. We are assume the function works, right? So if I assume the function works, that means that if I call fib on n minus 1, I'm believing that it's going to give me, the right answer. If I assume the function works again and I call it on fib n minus 2, I'm assuming it gives me the right answer. Then I can combine both of them to get fib of n, right? And that works perfectly. So this is just one way to think about it. So I just want you to look at something called the recurrence relation. Now let's go back to the question I gave us to do. I'm going to show you another way of, I'm going to show you why BP is cool, right? So if you look at this thing here, right, we drew the table out that if you compute this fib n minus 1 and fib n minus 2, they're going to have overlappings, right? Overlappings, and we don't want to waste time computing those things. So if I show you Fibonacci number, let's say DP, let's see if we get some images here. I want to show you how they overlap. Okay, so let's look at this guy here. So we're doing fib 6, right? And you can see that fib 6 means compute fib 5 and fib 4 and then add them together, right? Then fib 5 is compute this and add them together. But you can see there's fib 4 here and there's fib 4 here, right? and see fib as a function, right? Just need it to be a function. So you call the function on 4, call the function on 4, right? And that's like duplicate work, and nobody wants to do this, right? You waste so much compute, like you waste so much time. So when we compute for 1, let's assume this is the first one we compute. When we get to fib 4, we want to be able to use, the solution we got from here, right? In the same way, if you computed this guy and you get here, like whichever was computed first, you want to compute the other, right? So that's why we memorize. So that's the importance of memoization, which we talked about. Prevents you from doing, duplicate work or unnecessary work, right? So if you take a look at this guy here, right? This guy is going to do unnecessary work, right? Because he's going to call fib of, fib 5 here. Then he's going to do all the work. Then going to also call fib 4 intentionally. Then he's going to do all the work, right? And that is wrong, right? That's not something you want to do, right? So what you do is that you cache or you memorize, right? And we said there are ways of memorizing. One way, if you're using Python, I'm gonna say one reason why Python is cool. You can just use the LRE cache here. We will talk about caches later when we do like system stuff, right? So you can just do caches here with your, your max size and plan. You don't actually even need to know like max size, and you can actually create your own, right? But you import from func tools. But people, I don't know who use this. Like manually, you can actually build your own cache, right? You can just have something here, right? You can just be like, they usually use inner functions. So usually what you do, let's just use an inner function here, right? And you'll be like, okay, I'm going to pass n to it. Then I'll check if n in memo, right? Just a variable, a dictionary, right? Then you return memo of n. I'm just caching this solution. I just want to show you how easy it is to cache the solution. Now I'll take this whole solution, then I'll put it inside here. Then before I return, right? Before I return any solution, I'm going to store it in my cache, right? Just like a dictionary, right? Let me just use lowercase n. So I'm just showing how I cache the solution. It's very simple. It's just that whenever you compute an answer, put it in some dictionary. We usually use a dictionary. I just use like matrices, but they're very weird people. Return memo of n like this, right? And then here you just return inner, right, of n. So we just cache this solution, right? So the caching thing is simple. It's just a matter of, having each time you compute an answer, right? So this is actually the solution for some fib n, right? Don't just return the answer. Put it in some dictionary, right? So the next time the recursive call is made, right, before you even come down here, you first check, hey, are you in the dictionary? Have I computed you before? And it's like, yes. Then I'm like, okay, return what I got for you, right? That's simply how to, memorize this. So if you don't want to use the functools one, just the simplest way to memorize. It's very simple. We use a dictionary. So usually you should initialize the dictionary here like this. And then that's basically how you memorize. But if you come to the bottom down one, you don't have to memorize anything, right? Because as you can see, like it's just like a formula. Just take the previous 2 elements and add, right? So that's why I'm like the bottom up is usually a clean code, right? It's usually clean code because this kind of like that, this like playing the role of the hash map you see here, right? Like this guy's like playing that role. You just go take a look at the previous 2 elements, then just add them, right? But this is like kind of different, right? So that is the thing about memoization. It prevents you from doing duplicate work. Okay, now let's go to the next thing about recurrence relation. As I said, that's like the core. So now let's look at this question here. So this question, did everyone get time to read this question? If you didn't, let me give you 30 extra seconds to just read this question again. I just wanted to touch on products of array except self, recurrence relation again. And I want to just show you something interesting here. So please take a few seconds to read this question. You can read through the solution if you want. I just wanted to even read just one part of the solution like this, or maybe like this. Just one part, because this is a recurrence relation. This thing, I just want to show you this thing here. Okay, so let's go back to the question. It says you're given an array of integers, right? So this is an array of integers. I want you to return another list of integers where the number at that index is a product of all numbers except that number. So for instance, so if I take 24 here, 24 is equal to, all the product of all the numbers here, right? Because 24 is the first element. So multiply everything else except the first element, right? So at index 0, the answer is 24 because you can multiply all the elements except, the element at index 0. If I take 8, so this 8 here is the answer for 3. That is multiply all elements except 3. Does that make sense? Does the question make sense to everyone? If it makes sense, can say, yeah, I'll put something in the chat. I want to make sure people are following. If it makes sense, let me know. Before we go into the solution, does this make sense? You can react with it, an emoji or something. Good. Now let's go. People said it makes sense. So one solution, one way to solve this question is we're like, okay, when we get to every number, right? For every number, we're going to create 2 things called left and right, right? Left and right. So for every number, we're going to compute the left product. So what do I mean by left product? So if I take 3, I'm going to compute its left product will be 2 times 1, right? So if I take one's left product is like one itself, right? I mean, we use one because one is the multiplicative identity, right? So then if I take two, its left product is just one. If I take three, its left product, why is this thing is even? If I take three, its left product is everything multiplying, on its left. That's 2 times 1. If I take 4, its left product is 3 times 2 times 1, right? Does the left product thing make sense? Then the same thing for right product, right? So right product, so yeah, the right product of 2, right, is 3 times 4, right? The right product of 3 is just 4. Right product of 1, right, is 2 times 3 times 4. So that's what you're seeing here, right? So that's basically what these two things want to do. So then let's try to write the code to do this. So the code to do this is we're like, okay, so let's focus on the left one first. We want to ignore, the first one, but one itself is like, 1. I mean, one has no element to its left. So we just say, okay, let it be 1, right? Then we start from the next one, right? Then we are like 2. So 2, somebody's thinking, why don't we use 2 for loops, right? We can use 2 for loops. So this is a part I want you to get. So we could have been like this. We can be like for, let's say for j in range, right? This is something we could have been like for j in range, I, right? We be like left of I, right, times, let me even make it cleaner. Let's put some temporary variable here. Let's just make it 1. Then we like temp times equals, nums of j, right? So this is a perfect way to do this question, right? Like to compute the left sum. That is, if I'm at 3, what I want to do is I want to start from here, right? Then multiply all the numbers here, right? I want to start from 0, then do 1 times 2, right? Then I'll just put the answer, to be temp. Then after that, I'll just assign, left of I to be temp. Does this one I just wrote make sense to everyone, right? So like if I'm at 4 here, right? What I did, I just start from here. I multiply 1 times 2 times 3, right? Then after that, I'll put that answer as, the answer for 4. Does that make sense here? Does this make sense? Does this code make sense? Does this make sense? It could be wrong, I don't know, but I just want like the understanding, right? Does this code make sense, everyone? Does this code make sense? Does this code make sense? Before we proceed, does this make sense?
Yes, please.
Okay, it makes sense for at least one person. The others, does it make sense? I'm just saying, if I want to compute the left sum, right, like the product of all the elements on the left, right? So if I take the number, let's say I is where I currently am, then I'll start from the previous, and I'll start from 0, right? That's what I'm doing here for j in range I, right? That's like start from 0, then multiply every number at j, by temp, right? So temp starts at 1, so you'll be 1 times 1, then it'll be 1 times 2, then to be here to be 2 times 3, then you assign that one, right? But you see, this is an n squared thing, right? It's an n squared thing. And the other thing to note is that before I go to temp of 4, before I go to left of 4, I've computed left of 1, left of 2, left of 3, right? And that becomes like kind of tricky, right? Do people see it? People are probably not seeing it. So let me sketch what I want to say here. So actually, let me write on my thing, my writing thing. Let me write. I think that'll make it easier to notice. Give me a second. I'm installing a plugin. Okay. I think it will be easier if I. Okay. I just want to show you like how recurrence relation can really optimize your code. You don't write everything from scratch. Give me a second. I'm just loading my screen share. Okay. All right, let's go. So can everyone see my screen? Can everyone see my screen? Wait, can people see my screen?
Yes.
Okay. So we're just going to see how. Oh, why is this thing being like this? Okay. So. Oh, sorry. Okay. So this is what I'm talking about. So assume. Wait, sorry. Give me a second. My pen needs to activate. Okay. So we are computing left, right? Left of sum. So assume nums. Assume nums is this 1, 2, 3, 4, right? 5. And we are computing, left. And we said left is, the product to the left of everything, right? So what is it clear? Is my screen clear?
Yeah, I can see.
like, but is it clear? I don't know if it's clear because I see it to be small on my end. So I don't know if it's clear to everyone.
Yeah, I think it's clear.
Okay, that's good. Maybe let me just make it this way. Okay, I think this is better. Okay, so this one we want to compute.
Okay, yeah, this is better.
Yeah, and we said left is simply the product of everything. So if one computes like left of 1, right, we usually make it 1 because there's no number to the left of 1. But then the left of 2 is a product of everything to the left of 2, right? So everything here, and that is like 1, right? Then we go to left of 3, right? Left of 3, we said is a product of everything here, right? Everything here. So one thing we can do, we can start from here and be like 1 times 2, right? And that gives us 2, right? Then we go to the left of 4. That's a product of everything here, right? See how I'm dealing, see the algorithm I'm using right now. Then I'll be like, okay, then start at 1, multiply 1 by 2, multiply 2 by 3, right? And that's, 6. Then I'll be like, okay, now to do left of 5. I'm like, okay, start at the first one times this, times this, times this, right? Does it make sense to everyone? So 1 times 2, 2 times 3, 6 times 6 times 4 is what? 24, right? And then I'm done, right? This is how we computed left. And this is perfect, right? And this is the code I first walked through, right? But then look at something here. Let's bring recurrence relations in here to make our lives easier. What we just did is actually an n-squared approach, right? Because each time we were at some number, right, we started from the end here, right, to compute every single thing, right? And that is actually an n-squared approach. But the question you should ask yourself is, when I was at, let's change this, when I was at, when I was at left of 4, when I wanted left of 4 here, right, I had already computed left of 3, right? I had already computed left of 3, I had already computed left of 2, I had already computed left of 1, right? That's where the power comes from. When you're at left of 4, you had computed all these things because your loop is moving this way, right? Does everyone understand this fact? That the time you were at left of 4, you had computed left of 3, right? Does that make sense to everyone? That you had computed left of 3. Okay, good. Now, if I had computed left of 3, so this is done, right? So let's just check mark, this is done. And when you had left of 3, you'd have computed left of 2, you're computed left of 1, right? And that's perfect. Now, the question is, how did I compute left of 3, right? Let's just use parenthesis left of 3. Left of 3 was simply 2 times 1, right? That is this whole thing here, right? The product of everything to the left of 3. And left of 4, right? Left of 4, it's simply 3 times 2 times 1. But then we can see that this 2 times 1, right? This, oops, sorry, this is 1, right? We can see that this 2 times 1 here, right, that you need for the left of 4 is already computed for left of 3. So instead of using some inner loop to go inside and, try to get everything from the start, why don't we just, pick up left of 3 and just multiply it by 3? That's the power of recurrence relation. So here, instead of using an inner loop, right? So the outer loop like this, for I in range, we start at 1. So let's say the length of nums, right? We can simply say that left of I, right? We can simply say the left of I is simply equal to, nums of I minus 1, right? So here we're computing left of 4, right? But left of 4 is, 3, we take 3, left of 4, so we take 3, that's nums of I minus 1, because I is standing at 4, times left of I minus 1, right? And that's the recurrence relation. So we don't need any inner for loop now. Why? Because when we're at left of 4, they already computed left of 3, and that's left of I minus 1, right? And then you just multiply it by, the number that is right before it. Does that make sense? Does this make sense? And this is what we call a recurrence relation all time. You don't need to use an inner for loop. So this one with a recurrence relation can really optimize your code, right? You don't need to start an inner for loop from, 0. You don't need to start computing everything because you have done all the compute power already, right? If you think about it, it's the same as how memoization works, right? Because if you think of it, left of 3, right? Left of 3 is equal to 1 times, 1 times is equal to 2 times left of 2, 2 times left of 2, right? And left of 4, right? Left of 4 is also equal to 3 times left of 3, right? 3 times left of 3, right? So if I've already computed left of 3 here, when I get to left of 4, I can just borrow that left of 3 here and then I fix it in and then we are done. So that's the power of another thing of recurrence relation. So that question there can actually be solved using DP, as we just did here, but there's another approach to that. Okay, now let's go back to some things we want to do today. We just want to go over a few dynamic programming problems and then we are done. All right, let me share my screen in the other way. But did that make sense, everyone? Did that make sense? Recurrent relation. How you just can use just some formula and everything just falls right into place. You don't have to compute things from scratch. Okay, if you have any question, feel free to ask. Okay, now let's look at some questions. I want to show you another cool question. That's actually, I think I should write it. I think it's easier if I write it. It makes sense. Oh, wait, I think it's easier if I write it. Like this question, I came across this question some time ago, and honestly, I was so impressed by the person thought about this question. Okay, it's loading a bit. Give it a few seconds. I know some of you here don't like bits manipulation, right? Don't like questions that involve like bits and binary and stuff. I mean, they're not common in interviews. Like in my experience, have I had bits manipulation questions before? I don't think so, but I think it's good to know because you never know what happens. I know some companies like asking bit. I know sometimes Google asks for like full time, but no problem. So now the number is like, we want to count, this is a question, we want to count the number of ones, right? The number of ones, right, in a number. In the binary representation of a number, in the binary representation of a number. Repro is just representation, right, of a number. So this is what I mean. If I give you the number 0, how many ones are there? We're doing a quiz. Number 0, how many numbers are there? How many ones are in the number 0? How many ones are in the number 0? Anyone? Can just say any number. Let me go.
0.
Good, 0, right? If I convert this guy to binary, it's still 0 and there's 1. What about 1? How many are there? I'm showing you how to solve a DP question. How many are there?
1.
1.
1, good. Then if I give you, if I give it to you, how many are there? If I give it to you. So if I first convert it to binary, 2 is what? 1, 0, right? 2 is 1, 0.
Yes.
Yeah.
So there are how many there? 1, right? Then I give you 3.
1.
If I give you 3, it's 2, right?
2.
If I give you 4, 4 is what? What is 4 again?
That's 1.
4 is 1.
Hmm.
Yeah. I'm really confused. Wait, how many are there again? It's 1, right?
Yes.
I think it's 1.
Yeah, it
Okay.
should be 1.
So
I
when you get
think.
a DP question, the first thing you should do, we're going about how to solve a DP problem. The first thing to do is what we just did. When I give you the question, right, try to first write out like 5 cases. I usually like write 5 or 6. The way I'm saying 5 cases is usually the first 2 or 3 are like base cases for you to know, right? Then the next 2 cases are going to show you, the patterns of how they are built, right? There's one question we touched on last week, climbing stairs. We're like, if you have like stairs like this, right? If you have stairs like this and you can take 1 or 2 steps, right? Let's say you have steps like you can take 1 or 2 steps at each point, right? How many ways can you climb the stairs? That's the question we'll do next, right? And if you do this thing we just did, it becomes so clear to you what a recurrence relation is. Okay, so now let's continue. So if I have a question, if I have something like this, I first do this and I'm like, okay, is there something particularly interesting about this, right? Is there anything interesting about this? Then someone will be like, yes, someone will be like, no. So is there anything interesting about what we have here? Like with the number 0, we had 1. With the number 1, we had 1. With 2, we had 1. With 3, we had 1, 1. With 4, we had 1, 0, 0. With 5, I think 5 is 1, 0, 1. We had 2, right? I can just write a couple more for you. So just take a look at this. Do you think there's anything interesting about this? Do you think there is anything interesting about this? I hope my math is not off though.
Yes.
Okay. Can anyone see anything interesting about this? So this is what we have now. So this is 3 and this is 2. Anything? It's fine to say you don't know. I think it's a bit tricky to actually figure it out, but so we can actually just go ahead and see. So if we take a look at this right now, right? If we take any number, right? If you take any number, so let's take the number. Let's take the number 4.
Okay.
If you take the number,
Sure.
if you take the number 4, right? So I can tell you that. Let's just use DP. It can be like the DP of 4, right? And I said always when you write DP, you should define what it means, right? So one way people they say opt, right? That is the optimal value of 4, right? So let's just say opt n. People are more used to DP. Let's just say we say DP of n is the number, right? Is the number of ones. Is the number of ones. Let's just use it ones in the binary representation. The binary representation of n, right? So that means that if I create DP to be a list of n elements, so let's say 0, I initialize, a list n, right? If each entry is 0, right? So if I say DP of 0, I mean the number of ones in the binary representation of 0. DP of 1, the number of binary representations of 1, right? So that's the step 2 of solving a DP problem, right? So it's this step 1, give out examples. Step 2, define, now we're using some kind of bottom-up thing, right? Step 2, define what DP means, right? You're like DP of n is the number of ones in the binary representation of n, right? So I can create DP to be a list of n numbers, where so each index, so DP of 0 means the number of ones in, I know it's kind of like normal sense to think about that. I'm just making it a bit formal, right? So then I can see that DP of I, some arbitrary I, right? So let's take DP of 4. You look at, if you take 4, you realize that if you take 4 and you divide 4 by 2, what do you get? You get 2. Can you see we are narrowing it down? If I take 4 and I divide 4 by 2, I get 2, right? Then check the number of ones.
Yes.
Binary representation of 2. And that is the same as DP of 2. So this is DP of 4. If I split it now, I get DP of 2, right? I get DP of 2. Then after that, I will consider, right, is 4 even or odd, right? If 4 is even, I will not do anything. If 4 is odd, I'll add +1. And that is the whole recurrence relation. So let's look at it here. So here, DP of I, right, is going to be DP of I divided by 2. Why are we doing divided by 2? I didn't divide by 2 because before I got to I, I'd have already solved for I over 2, right? Because that's how my for loop works. The for loop starts from I is equal to 0, I is equal to 1, right? It starts from the smaller ones, right? So to solve this bigger problem, we first solve a smaller problem, right? We'd have solved this already. So like the left thing we did, before we got to, DP of 4, like left of 4, we had already computed for left of 2. So using the smaller problems to solve the bigger sub problem, right? Plus, right? Plus, if it is odd, let's just write English here. If it is odd, we add +1. If it is even, you don't do anything, right? Just +0, right? You can just ignore it. So let's take a look at this thing and see. Let's take 2, right? Let's divide 2 by 1. What do we get? We get 1, right? If I divide 2 by 2, if you divide 2 by 2, divide 2 by 2, as we said here, this is a recurrence.
You get 1.
Yeah, good. You get 1. So, and 1, what is DP of 1? DP of 1 is 1, right? DP of 1 is 1. Then it's 2
Yes.
odd. 2 is even. So you get 1 plus 0, which is 1, as we have here. If we take 4, divide 4 by 2, what do you get? You get 2. How many ones are in 2? It's just 1. And 1 is even.
1.
You get 1, and that's the answer. Can anyone see how everything falls into place? Right? That is just how things fall into place. So that we don't have to write any for loop. You have to write a for loop. So here the for loop, so here the solution is something like this. So as we get it, you define DP. So we can just make it to be 0 times n, right? Then you fill in your base cases. So here the base cases we fill in are going to be these first two, 0 and 1, right? Because you realize that once you do for 0 and 1, everything can be built from 0 and 1, right? So I'm doing bottom-up approach now. So then we can, for DP of 0, right? We are like, there are only 0 ones in 0, right? Then DP of 1, right, is just, 1, right? So now the table looks like 0, 1, then the rest are zeros. Then I'll start my loop from 2, right? So for I in range, right? For I in range 2, right? Actually, this should go +1, right? For I in range to n plus 1, because you want you want the last element, like you want DP of n. You want DP index n, right? Indices, this is like 0 index, right? So DP of n. So here, DP of I, it's simply equal to DP of I divided by 2, divide the number by 2 and get how many zeros there are, plus, right? So yeah, we can use ternary operator, +1 if I mod 2 is 1, else 0. Please, this is just me writing like, if it is like odd, add 1. If it is even, add 0, right? Like, and this is basically the whole code. Then at the end, I can simply return DP of like the last element, right? Because the last one is going to be index n, right? And this is the whole code. Does this make sense? Does this make sense? If this is confusing, just tell me it's confusing. But does this make sense? And you see, once you have this recurrence relation, this is what we call a recurrence relation, you solve the question, right? So figuring this out is kind of like the main deal, right, for DP, like figuring this out. But if you write a few examples, somehow, I mean, the interviewer may give you a clue. This is actually not easy to come up with, honestly, I tell you. Like, this is not easy. When I first said, I was so impressed, right? Like, if you take DP of 6, right? If you take this guy here, divide 6 by 2, you get 3. So go and look at DP of 3. That has how many ones? 2 ones, right? Is 6 even or odd? Even. Then just add 0 to 2 and you get 2, right? And it just works, right? So that's just how it works. So DP. So this one way, that is, so 2 steps. First, write out some examples, make it make sense to you. Define what DP means. Here we said DP is the number of ones in the binary representation of n. Then we got a recurrence relation. DP, this is number 3. So DP of I, that is the number of ones in I, is equal to the number of ones in I divided by 2, plus if it's odd, add 1. If it's even, add 0, right? And then everything will flow naturally, right? Just use a for loop, right? Just initialize your DP table. just use a for loop and just fill it in, right? As you can see, this will be filling in the table. Then at the end, you want dp of n, right? You can just say return dp of n, but Python dp of n is the same as like, the last element, right? And then you are done. Does this make sense? Before we go to the next question. I know dp is a bit hard to, so this form of question works for nested for loops, right? I mean, can you use nested for loops to do this? Like someone can use nested, but okay, you really don't use nested for loops, right? Because you only need like one value. Like to compute dp of I, that is the number of ones in the binary representation of I. You just need, this guy here, right? Unless you want to use a nested for loop and be like for j in like range of I, like if j is equal to I divided by 2, right? And that is really not needed, right? So yeah, someone Idris, you can ask your question.
Please, with the even, you say you check if it is even, then you add 0. But if it is odd, you add 1.
Yeah.
Please try to check the number of ones in the number you have divided by, or you check with the whole number itself.
Yeah. So here is the number of ones in some number I, right? When like the number of ones in this number I is equal to the number of ones in the number I divided by 2, right? I divided by 2 here, right? Plus, if the current number I, right? If it's odd, right? If it's odd here, right? We add 1. Else we add 0, right? So you check if the current number is odd, right? If the current number I is odd, then we add 1. And if the current number is even, then you add 0, right? So here, so the only part where we use the I divided by 2 is this part here, right? That is the dp. So that's like, you have the main problem, that is dp of 4, right? But we said we use sub problems, right? Before you got to 4, you had already solved dp of 2, right? Because start from bottom, you can start from smaller incremental values. Now, if your number does not if you don't start from bottom, you're going to end up getting maximum recursion depth exceeded. So you always start from the smaller one. So you always solve the smaller one, dp of 2, and dp of 2 is what you have here, dp of I divided by 2, right? Then plus, so assume this thing here is a plus, then this thing you have here, if it's odd, plus 1, right? That is what we have here, right? If it's even, it's just 0, and then just add to get this. Does that make sense? So it's more like take the smaller one, then add them together to get like dp of 4, and 4 is bigger than 2, right? Does that make sense?
Yes.
Okay, good. Let's go on to the next question. So this one way of just doing this. Now let's do the climbing test one we talked about. So let's assume you have, and yeah, I know DP is a bit, tricky. Internships, some companies don't even add DP questions. Like Meta will specifically tell you, hey, you're not going to give DP questions. Many companies like Facebook won't ask, like many companies will ask, because it's a bit, hard to wrap your head around unless like you've really learned it. But I think it's really good to know. It really like improves your thinking. Also, some companies ask though, by the way. Yeah. So let's assume you have this, probably the last question. We're actually behind time. I wanted us to do a couple more, but you realize they actually follow kind of like a very similar pattern. When we did backtracking, you can actually convert that knapsack question also to what do you call dynamic programming. That is if they add values to it. So like we did, what do you call it? When we did like the interval question, if you remember last week, right? We're like, how many intervals should you choose, right? And it was easy, just sort them and choose the ones that end first. But the moment we added values, right, that each interval has a value, we realize that you can't just make that decision. You have to try all possible combinations, and then DP comes in, right? The same for the knapsack question. Okay, now let's do this last example. So this question is like, you want to take stairs, right? So this is like, let's say 1. How do I number these steps? So this is stair 0, this is stair 1, stair 2, stair 3, 4, 5, 6, 7, right? And I want to see how many ways we can get to the topmost portion, how many ways we can get to this part. When you can either take 1 step, right, or 2 steps. So this is, the number of steps you can take, right? And I want to show you how dynamic programming can be like easily thought through to solve a question like this. Okay, so as we said, the first thing is that you ask examples, right? You get examples for your question. So you're like, okay, what if I had, 0 steps, right? That's obviously 0, right? So we can even first define DP first. Let DP of, let's say DP of I be the number of ways. You can just take the question, just, use that question. Be the number of ways to get to stair, right? Stair I, right? Does this make sense? We've defined what DP of I means, right? So like DP of I is the number of ways to get to the stair I, right? They're like, okay, so what is DP of 0? That's the question we ask ourselves. How many ways can we get to stair 0, right? There's only 0 ways, right? If there are 0 stairs, right, Like there's literally like nothing, right? Zero. This is even a useless base case, I think. If there's only one stair, right? How many ways can we get to stair one, right? You can only take how many do you think can get to stair one? How many ways? We can only take one step to get to stair one, right? You can't take
One.
two steps is out of bounds or something, right? So there's only one way. Let's put that down. What about DP of 2? What's DP of 2? How many ways can it get to stair 2? So we want to get to the stairs, right? So we can first do 1, right? 1, 1, right? Or we can just take the full 2 steps, right? So there are 2 ways. Does this make sense? Does this make sense?
Yes.
DP of 2. Good. Now, then someone will be like, how about DP of 3, right? So always, like, it's so important to give examples. I've seen it to be like so helpful. So DP of 3, how many can we get to stair 3? Then let's use a different color to do that. So stair 3, somebody will be like, okay, I'll take 1 here, right? And then I'll take 1 here, and then I'll take 1 here, right? So I've got 1 way now. Somebody will be like, oh no, don't do that. Just take 2 here, right? Just take 2 here, and then take 1 here. Somebody's like, no. So we've got 1. Somebody will be like, no, don't do that. First take 1 here. I know if somebody can see some recurrence relation forming, then take 2 here, right? And then I've got another 1 way, right? And I think those are all the ways, right? And that gives you 3 ways, right? So here we go 3 ways. Have you seen the recurrence relation forming? Like a recurrence relation just formed.
Yeah.
If you take a look at this. So then, okay, then let's take the next one. Let's take DP of 4, right? Let's take DP of 4. We're like, how many ways can I get to the 4th step? Let's use a different color and try that too. So let's take black, right? I like black, not because I'm black though. Well, I am. Okay, then we can be like, okay, 4. Let's first take 1 here. This is getting messy. Let's take 1 here. Oops, what is happening? You're like, okay, let's come to stair 1 step to stair 1. Because we can take 1 step, so why not? Another 1 step to stair 2, right? Then we are like another 1 step to stair 3, right? Like another 1 step to stair 4. We are here, so we've got 1 way, right? Someone's like, no, don't do that. Take 2, 2, right? So we take 2 to 1 to 2, then 2 to 4, right? So that's 1 way. Definitely like, no, don't do that. Take 1 to 1, right? So take 1, 2, 1. So we've got 1 way, right? Then somebody's like, no, don't do that. Take, you can just think about it. Take 2, 1, 1, right? 2, 1, 1, and so on and so forth. And trust me, at the end you end up getting 5, I think. I think so. Wait, we can actually try it and see. So we get 1. You can do from stair. Let's just clean this up and let's just make it clean. I don't know. I'm even getting confused with my own thing. Okay, let's clean this thing up. Well, I want everyone to get the picture in their minds. So let's just clean this up. And let's do for only 4. I want to keep this guy. Okay. After 4, we're done. You just see the recurrence relation so beautiful. Now, I know people think they've seen it, but let's just take our time. Okay, so let's see.
Sure.
So we're doing 4, right? So 4, we can come here, right? 1, 1, 1, 1. So this is 1 way, right? So let's note that down. 1 plus, right? Then we can also do 1. We can do 1, 2, 1, right? So 1. Then we can also do 2. We can do 2, 1, 1, right? What else can we do? Anyone? So we did 1. I beg you push help me. I'll say 1, 1, 1, 1. We've done 1.
1, 1, 2, I think. 1, 1, 2.
Okay, 1, 1, 2, right? 2, 1, 1. Yeah, we can also do 1, 1, 2, right? 1, 1, 2. Okay, we can also do 1, 1, 2, right? So we go 1 more. What else can we do? 1, 1, 2. We can also do 2, 2.
Can we exit 3?
We've not done 2. We've not done 2, 2, right? So if we do 2, 2, 2, 2, right? So if we do 2, 2, is there any way we haven't tried? Is there any way we have not tried? I think that's all right. That's all right.
I think that's all.
Right. So how many ways do we have? 1, 2, 3, 4, 5, right? Now you can tell me you've seen the recurrence relation, right? So if we did DP, so what do you think is the recurrence relation? What do you think is the recurrence relation? The DP of I to get the number of ways to get to the I floor, it's equal to, just look at the example. You don't need to overthink it, right? If we take, what do you call it? If you take 3, right? You can even start at here. If you take 3, right? If you take 3, I probably can make this case like 1, I don't know. If you take 3, it's just 2 plus 1, right? And that gives you 3. If you take 5, it's just 3 plus 2, that gives you 5. So that's like DP of I minus 1. That's the number of ways to get to the floor that is right before it, plus the number of ways to get to this floor that is 2 before it, right? And that's basically it, right? So, and that's it. We're actually done with the question. Like in this, once you have the recurrence looking, you can just write out the code for I in range, right? For I in range, maybe 2 to maybe n, right? We can even do n plus 1 because we want to get to the n floor. dp of I, it's simply equal to dp of I minus 1 plus dp of I minus 2, right? And that is all. Other than you can just return dp of minus 1 or dp of n. Any of them works, right? And that is basically how it works. If you're wrong, that because we didn't probably set up our base cases well, but that's basically how you do the staircase problem, right? And that is just how it works. Does this make sense to everyone? To solve a DP problem, get some examples down, try to see if you can, visualize the example, define what DP means, and then, just try to do it. But if you don't set up the examples right, you probably make a mistake and then get it wrong. If you do maybe DP of 5, it may be 8. I don't know, somebody can try it and see. If you do how many ways to get to 5, you can do 1, 1, 1, 1, 1, right? Then we can do 1, 2, 2, 1. We can do 1, 1, 2, 1. We can do 1, 2, 2. You can also do 2, 1, 2. You can do 1. We won't finish this today. Okay, but there'll probably be 8. I don't know. So yeah, but does everyone have, maybe we made a mistake somewhere, I don't know. But does anyone have a good feel of like setting up a recurring solution, just using it to compute your DP solution? Okay, we're actually behind time a bit, but we will pause here on dynamic programming. There's just, if you could, I think it's good to think about it. We've not really done, I mean, I've shown some memoization, but I think we can do more in memoization. The memoization we've done so far, let me touch on this, and then we are done. So you see what we've been doing, we've just been memoizing or starting out of solution in a one-dimensional, like structure, right? Like just DP is just going to be like a list like this, right? This is what DP is going to be. Like the one, even the memoization we did, right? That is the hash map, is just going to be like key value pairs, right? Just like this. Then maybe we're like, maybe DP on like this same question. Like this question just can also be solved like using recursion, right? So recursion will simply be like this: def number of stairs, right, of n. So if maybe n is 1, if n is 1, return, like there's only one way you can get to it. If n is 2, right? If n is 2, there are 2 ways, right? Return 2, right? Then we can be like return. Then for 3 onwards, we can be like return the we call this number, right? We call number of n minus 1 plus number of n minus 2. This is just the recursive solution. Very clean, but not just memorize this, right? Because you can see that this guy and this guy will have some common function calls, right? So you want to memorize this, right? So the memorization of this is simple. Just throw it in. We said before you return, store the answer in a dictionary, right? So memo of n, right, is equal to this. Then you can return memo of n, right? And then before you start computing any of these, you check if n in memo, right? If it's in your DP or memo, whatever you call your dictionary, you can return memo of n. So that we are done. And this is how you memorize this thing. And that's all right. So you realize that this dictionary is also going to be like the key is going to be like an integer like n, then the value is going to be like 24, it's going to be a number. These are all one-dimensional, right? Doesn't get to a question where you actually get two-dimensional DPs, right? Two-dimensional DPs. Let me show you one way. So one way to do it is, so we used like a certain, I don't know if we still have the image here when we started DP. Yeah, so look at this thing. When we did this example some time ago, right? Right. This is actually two-dimensional, DP, right? Two-dimensional in the sense that the keys are not just going to be one number, they're actually going to be like 2 elements in, right? Okay, we have both a row, right? A row and a column, right? So our dictionary is going to be something like, so I don't know, some of you were not here, but this is like, so let's assume number of ways to get to this point, right? Number of ways to get to this point. Number of ways to get to this point. Someone is like, okay, I can assume you can go in 4 directions, right? You can be like, I can go to this part, right? Then I'll go to this part, then I'll come here, right? Someone is like, okay, I'll go to this part, then I'll come to this part, then I'll go to this part again, right? Then I'll come here. So as you can see, like the first path, right? The first path took this part, and here, and you were done. Then the next part took this part, but they get to this part again. The question is, should I compute, the energy spent, to get to this part again? No, because the first path already made me compute it. So I can use that one, right? I can use that one. So when that happens, you have to also memorize that, right? So the memo, right, or the cache or the DP for this thing looks something like this. It looks something like this. So you can have your row table here. It looks like a grid, and that's 2-dimensional. So that's like something like this, right? Then usually you have like the row here, you have like the column here, then like, just like that. If it's use a dictionary, you can just make the keys a tuple, row, comma, column, right? Then maybe the answer here, right? Don't worry, we can touch on more examples in August or stuff like that. But today I just wanted to get like the intuition for DP. Okay, probably send a few questions that people can actually think through. But really next week, I'm thinking we circle back to complete the last 2 data structures we have left, tries and graphs. That's like the last 2 we have. Then we'll probably end up with some just slight extensions like nested list and matrices. So go next week. I'm thinking we either do tries first and complete tries. Then maybe go into graphs. Tries are relatively easier in some sense, but they're very powerful data structure. And then we should be good. Any questions? Any questions? Any questions? I really hope I recorded this thing. I hope so. Any questions? Okay, so that is it for today. You can try the questions we just did today on LeetCode, like number of ways of climbing stairs, or like any of those like Fibonacci. Or you see these same patterns we used. Get a recurrence relation, put things together, and you are there. Okay. All right. I see. Okay, let's meet God willing Sunday and let's go over tries and graphs. Okay, bye. All right.
Bye.